Hello, my name is Yuli Bilik. I'm a professor at the School of Mathematics and Statistics at Carleton University. It is my pleasure to welcome here today two scientists from the Defense Research and Development Canada, David Waller and Mohamed Abdelaziz, who will tell us about the work that they are doing and about career pathways for graduates with degrees in mathematics and statistics. I apologize that due to a technical oversight, the first 2 minutes of David Waller's presentation was not recorded. Now it's to David Waller and Mohamed Abdelaziz. Welcome.
That first introduction to research showed me one of the key lessons I've learned along the way, that knowing how to program a computer is exceedingly important. Doesn't matter 30 years ago or today, you really can't get much done without doing a significant amount of programming in the realm of science or data analysis. So after doing my bachelor's degree, which by the way was at the University of Alberta in Edmonton, I then moved to Queen's University, where I did a master's degree in nuclear physics. And this was a nice change because now you get paid for school to be a graduate student. So I'm not sure what fraction of you who are online are grad students versus undergrads, but hopefully you're getting at least some money too while you do your studies at Carleton. So while I was at Queen's University, I worked on an experiment called the Submarine Neutrino Observatory, or SNOW Lab for short. So there we were studying subatomic particles that are produced in the sun in nuclear reactions right in the core of the sun. And those particles go streaming out from the center of the sun, and they're really, really hard to detect because they pass through most matter like it's not even there. So to give you a sense of how easily they pass through matter, a typical neutrino will pass through about 1 light year of lead before it bumps into anything or gets deflected. So they are really tricky to detect as a result. So we built a very sensitive detector in the bottom of a mine just outside of Sudbury, and then collected the data. And then the reoccurring theme of the need to do lots of programming in order to analyze the data came up again. After I did my master's at Queen's, I moved just a little bit north, up the 416 to Ottawa, and moved to Carleton to do my PhD. And my experiment that I worked on, again in subatomic physics, was just outside of Geneva at a lab called CERN. So it's the world's largest particle physics, or the world's largest physics experiment. Can you see my cursor on the screen? Yeah. So the picture on the right here that I have my mouse over is an aerial photo of the French and Swiss countryside just outside of Geneva. So this white circle here is the particle accelerator that's about 100 meters underground, just outside of Geneva. And the particle accelerator is 27 kilometers around. So just for a sense of scale, this white strip over here is the Geneva airport. So it's an extremely large place. And this photo on the left here, small photo, is of what the beam line, where they accelerate the particles, looks like at CERN. And then on the bottom right is a picture of the type of detectors that we were using to detect subatomic particles that are created in these big collisions that are made in the accelerator. And just for a sense of scale, that little teeny figure at the bottom, it is a person. So these particle detectors, or the modern ones these days, are about 20 meters tall and about 60 meters long. So huge things, huge machines that produce lots and lots of data. And in my case, I was studying subatomic particles called quarks. They're the things that make up neutrons and protons. And not surprisingly, again, dealing with very large amounts of data. These days, it's about a terabyte per second that gets produced at these experiments. It requires lots of computing power, so lots of programming, and then, of course, applying a lot of statistics to make sense of all the data that comes out of the apparatus. So this was great training. Well, to finally get a job, or sort of a job, which led me to continue at Carleton University, but as a postdoctoral researcher. So this is the job that people often get after they're done their PhD. So in typically 2 years or more. And in my case, I worked for 3 years, again, on this experiment called the Submarine Neutrino Observatory. And by this point, there was lots more data to analyze, so lots more stats, lots more programming. And this turned out to be an especially exciting experiment because the head of our experiment, shown here, Art McDonald is his name, was a professor at Queen's University, ended up winning the Nobel Prize in physics in 2015 for this work. And the number 2 person running the experiment was a faculty at Carleton, David Sinclair. And Carleton had a very big group involved in this experiment as well. So it's definitely one of the most successful science experiments that ever happened, not just in Carleton, but in Canada. Okay, next slide. So that was I said that was technically a job. It was a job. I did get paid. I was no longer a student, but I was still at the university, and just short term. So what I call my first real job was working for Defense Research and Development Canada. So there, I started working at the Center for Operational Research and Analysis. So basically, at this place, we hire people from all sorts of backgrounds, but we especially hire people with mathematics and statistics backgrounds, because it's basically applying math and stats to operational or military problems. And the problem that I first started working on was Arctic surveillance. So this required building computer models of different types of surveillance systems that Canada can use to keep track of what goes on in the north, running simulations, and then finally doing mathematical optimization to try and make the best use of resources, finite resources that we have for keeping track of what's going on in Canada's north. And the Center for Operational Research and Analysis, where I started, is one of 7 research centers that make up Defense Research and Development Canada. So they're spread across the country from southern Alberta all the way to the East Coast and Halifax, and many in between, though they tend to be clustered around Ottawa is the highest density, including where I was and currently am again, Center for Operational Research and Analysis. So after doing OR, operational research, for 3 years, I switched gears, going from applied math and stats back to my roots as a physicist. Oops, sorry about that. So what I spent most of my time working on were various applications of measuring something called cosmic ray muons, all with the goal of improving national security. So what a muon is a subatomic particle that gets created when cosmic rays from outer space crash into the Earth. That they don't last for long, just fractions of a second, but they're traveling very, very close to the speed of light. So they travel all the way from the upper atmosphere all the way down to the Earth's surface. And they have an interesting property, depending on what you want, what you're doing, that they are very, very penetrating. So they're thousands, tens of thousand times more penetrating than an X-ray. So what we were working on for this project that's shown on the right-hand side, which was actually built at Carleton University, was a system that carefully measures where a muon enters some object that you're interested in. In this case, the object that we had in the middle of our muon system was an air cargo container. So what we were doing was we built a system that can look for smuggled nuclear material or material that can make up nuclear weapons like uranium or plutonium. And a normal X-ray machine can't differentiate between regular dense stuff like steel or lead versus really dense stuff like uranium or plutonium. So with muons, stuff like steel. It tends to be relatively transparent. It doesn't, basically the muons are so high energy, they pass right through the steel. But when they pass through the uranium or plutonium, because they're so dense, they tend to get deflected. So the system that we built at Carleton carefully measured muons that come from above, for the most part, so from the sky above, measure them very carefully before they go into the air cargo container, and then carefully measure where they exit the cargo container. And when the muon gets deflected or scattered inside this cargo container a lot, it's probably, very possibly, because there's uranium or plutonium on the inside. So it basically works like a CT scan does, like a whole body X-ray that builds a 3D image of what's inside your body. But in this case, we're using muons to build a 3D image of what's inside an air cargo container. And the idea was this could also be applied to other larger objects like a sea cargo container, like you see that come into Canada's ports. And the reason for doing this is because it's actually really difficult to see nuclear material if someone actually tried to smuggle it. And that's obviously a big concern, because that's the type of material that you can make a nuclear weapon out of. So globally, there's a demand to come up with some system that can detect smuggled nuclear material. So we built this prototype at Carleton. It worked, and it's now in further development and testing at Chalk River Labs, or Canadian Nuclear Labs, it's now called, in Chalk River, just a couple hours down the road, down highway number 17, if memory serves correct. So the other thing that we did with muons during this work was to devise or come up with a system that might be able to detect extreme space weather, or better yet, an early warning system for extreme space weather. So basically, extreme space weather happens when the sun has a very active and bad day and spits off a giant ball of hot magnetized gas, which is called a coronal mass ejection. So sometimes people refer to them as solar flares. The two things are related, not quite the same thing, but they're closely related. So when a coronal mass ejection is ejected by the sun, and it happens to hit the Earth, it can actually have it could have quite devastating effects if it was a worst case scenario, where a large portion of the Earth's, or a section of a continent's electrical grid could be taken out. And it depending on the circumstances, it could actually take years to get the electrical grid back together again if it was an extreme space weather event. And these events have occurred before in Earth's history, but they just fortunately happened before mass electrification of the globe. So if you had early warning that something like this could happen, you could adjust your electrical grid so that the consequences weren't too devastating. And where the muons come into this is if you have this big hot ball of magnetized gas that's somewhere between the sun and the Earth, if you're able to look up into the sky and measure where all the muons are coming from, the muons will tend to get deflected away from the Earth by this coronal mass ejection. So in principle, you could have up to 12 or 24-hour warning that you're about to have an extremely bad day thanks to the sun. So again, common theme here. This was a lot of statistics, a lot of applied math to do image processing, and for the searching for smuggled nuclear material, we also used some machine learning to try and improve the algorithms for detecting the nuclear material. All right, next slide. So I actually spent 10 years working in this area of applied nuclear physics for national security reasons. And I think one of the most interesting experiences I had while doing all this research was actually going on a trip with some of Canada's special forces people for training at the Chernobyl nuclear plant. So this picture of Chernobyl is in the background. And we got to do all sorts of interesting measurements in the field, in the contaminated area, or what is still a very contaminated area close to Chernobyl. So not too many jobs do you get to do something interesting like that. That was quite memorable. Okay, next, after doing almost 10 years of applied nuclear physics and particle physics, I made a temporary switch into the realm of cyber defense. And in particular, I was working on something called offensive cyber operations. And unfortunately, this is about all I can show you. is just a cartoon. As you can probably imagine, most of the work that gets done in this area is classified. And that is a feature of working for DRDC, is that some, not actually, the majority is unclassified that we do. So we do get to publish in journals and go to conferences and present, but some of it is classified. Okay, and the last slide I'll show you, the last slide with science content, math content, is for the thing that I've been working on most recently. So for the last 3 years, I returned to the Center for Operational Research and Analysis as a manager. So I have 5 teams that I work with doing applied math and stats for various parts of the Department of National Defense. And when the pandemic hit in March of last year, a number of the scientists who I work with, and scientists actually outside of my immediate group, started to work on COVID-related support to the military. So in particular, early on, the military needed to make decisions about what was the safest way to continue conducting military operations, which included things like going into the long-term care homes in Ontario and Quebec, because the outbreaks were so bad there that the normal staff couldn't handle it. So Canadian medical officers and medical technicians helped out. And regular national defense operations have to continue, like ships still have to go to sea, planes need to fly around, etc. And in the early days, there was no good way of quantifying what the risk was to Canada's sailors, airmen, and soldiers whenever they took part in any military activities. So what the team of 20 scientists did was to come up with a number of tools to help quantify the risk posed by COVID. The one that's in the bottom left-hand corner here is just a screen capture, was a map we made of the globe that divides the world into about 3,500 different geographic regions and takes publicly accessible data on COVID case rates to estimate what the true prevalence is of COVID in each of these geographic regions. And then it applies epidemiological models to this data to make a forecast into time for how the rate of COVID is changing. So this is old data now, but from the city of Ottawa. So you can see as time goes on, the prevalence of COVID goes up and down over time. And knowing the prevalence of COVID helps the military to decide whether or not to send out 250 sailors on a ship or not, or if they do send them out, to determine if they should be quarantining for a length of time before, or if they should be getting tested a number of times before they go out to sea. Because if there's an outbreak on a naval vessel in the middle of the ocean, there's no one there to help you, not immediately anyway. So you really want to understand the risks that can be posed by COVID. So we were able to develop a number of tools along with medical doctors who work for the Canadian Forces and infectious disease experts. So being able to work as a multidisciplinary team led to some very useful tools. And throughout the pandemic, we've been meeting with other federal government researchers from a number of different government departments, particularly from Public Health Agency Canada, who's responsible as the lead agency during a pandemic. And they were so happy with some of the tools that we created that they have shared them with the World Health Organization so that other countries can be better informed when they make decisions about COVID risk for the type of scenarios that we were looking at. And actually just earlier today, a team of our scientists gave updated modeling results to the commander of Canada's Navy and our Surgeon General. Because as the pandemic goes on and things like the Delta variant occur, you keep on having to redo these calculations to update our understanding of what the risks are posed to people. So it's been exhausting work because the pandemic isn't going anywhere quite yet, but it's been very, very fulfilling to make a real world difference to the decisions that the military commanders have to make. So to conclude with, as I hope you gather from just a little snapshot of my career at Defense Research and Development Canada, it's hard to predict what you do when you're a research scientist working for DRDC, but I can guarantee that it's been exciting, it's been challenging, lots of interesting technical problems to deal with, but it's all been for the purpose of making Canada more secure, and of course it's involved lots of math, lots of stats, and lots of programming, because there's lots of data to make sense of. So thank you very much for your patience. And as promised, on the very last slide, I've got my work email address, david.waller2 at forces.gc.ca. So if you are interested in applying for a job with us, either in operational research or data science, basically anyone with a strong math background, with a minimum of a master's for a long-term job, but for undergrads, we do hire students and interns, and yeah, we do hire non-research scientists as well. So if you're interested, please send me a CV. So at this point, I will stop sharing the screen so that Mohammed can have a turn.
Thank you, David, for a very interesting presentation. I think we'll probably keep the questions until the end, so after Mohammed's talk. Mohammed, please.
Absolutely. Okay, let's go. Okay, can you see my screen, full screen?
Yes,
it's
okay, all good.
Perfect. Okay, so hi everyone. So I'm Mohammed Abdulaziz, and I'm actually a new grad at DRDC. I only started 6-7 months ago. I started in February, so my presentation is going to be a little bit different than David's. I'm just going to talk a little bit about my background, couple of projects that I started working at DRDC, so nothing in depth because I just started working, but I'll also provide a little bit of background on one of the fields that I'm working in, which is machine learning, which is, I believe, is a prime field for mathematicians and statisticians to go into. Okay, so just to get started, I'm a Carleton University student. Actually, I'm still doing my PhD there in the final stages, trying to finish up this semester, but we'll see. As you know, research, sometimes things work out, sometimes it doesn't, and we'll just keep going at it. But I have my Bachelor of Engineering is in Biomedical and Electrical Engineering, my Master of Applied Science is Biomedical, and my PhD is in Electrical Computer Engineering. But actually, it's my project is still in the biomedical field. So my PhD project was on, or is on, I'm already in the mentality of I'm done, but it still is my PhD project is on detection of atrial fibrillation in compressively sensed ECG. So atrial fibrillation is a cardiac condition where the atria, or the top chambers of the heart, are fibrillating, which means that they're not contracting correctly. And ECG is electrocardiogram, which is the electrical signals of the heart, and you can see that in the right-hand side. That this image is essentially a strip of ECG that doctors would typically record of a patient. What compressive sensing is, as the name suggests, is trying to sample the data as it comes in. Now that this data is biological data, so it's analog data, and trying to digitize it, so turn it into what a computer could understand, but trying to compress it as it's being sensed. And the way it looks like is actually on the bottom right. So X is, let's say, the ECG, and it's multiplied by matrix to equal a compressed vector. So some of the questions that I'm answering in my project is, what are the features that would indicate atrial fibrillation in ECG? Are these features still available after we compress the ECG? Because this is a lossy compression. So we lose information. So is the information still there or not? How much can ECG be compressed before it's usable? And what is the impact of noise on the detection of atrial fibrillation from ECG? And by noise here, I mean it could be biological noise. So it could be someone flexing their muscles, and that would affect the ECG. Or it could be cell phones, which would also impact the ECG. And that's why in hospitals, they used to say, and I believe they still do, it's important to not have your cell phone on next to medical devices, because it could impact their operation. But I joined DRDC in February, and I started working on other projects. So here, just a few of them, and as I mentioned, I just started, so I don't have a lot of information on these projects, but there's a trend that's going to come up, and that's what I'm going to talk about. So first of all, I did a data challenge, which was to identify the gender of the speaker from a voice recording. And that was a very interesting challenge, because we're provided with videos and voice recordings from cell phones and essentially other data that could be exploited in order to better secure the Canadian borders and Canada in general. Well, actually, this data challenge was across multiple countries, so it was for the security of multiple countries. And I mentioned, well, how about we could identify the gender maybe of the speaker, and from there we could identify maybe the emotions and maybe background noises. So we'll have a more holistic information on who's talking, who they are, who are they, and what is happening around them. So in order to address the challenge, I used DSP, or digital signal processing techniques, which are mathematical techniques that specifically target working with 1D signals, such as filtering, removing any extra noise, transforming into other representations, such as Fourier transform, or wavelet transforms, or DCTs, the discrete cosine transforms. So these are transforming data into other domains is quite important to highlight certain features and information in the data. I also started working on optical character recognition. So this is reading essentially handwriting or handwritten notes. And it's important because as you could take pictures with cell phones, or you'll be able to understand written text from images that have been taken by individuals, whether that's on social media or just for personal use. And the idea is we'll be able to understand some of the information that we're getting in. Instead of visual form, we'll have it in a computer understandable format. I also been developing a concept for what's known as the Joint Operations Fusion Lab. And this lab is currently being set up in order to fuse data from multiple sources, whether it's sensors that are in space, or there are sensors down in submarines. It's trying to collect all of this data and provide a holistic idea and view of what is happening around us, which is known as situational awareness. What is happening around the Canadian borders, what's happening in space and in the air domain, any other data that could be collected, or it could be deployed more in an operations, in an operational perspective, which is, hey, there's a conflict that's happening somewhere, and the Canadian Army is going to, or the armed forces are going to deploy in order to protect or secure something. Having this holistic information coming from different sources fused together is what's needed, really. And finally, it's developing a framework for the development of secure machine learning applications. As you might know, machine learning is quite expanding into different fields. And if you don't know machine learning, that's actually what I'm going to give a quick intro on. But machine learning is prolific now in all applications. And from an armed forces perspective, it is quite important to be able to have a secure machine learning application that is not going to be manipulated by the enemy or by a bad actor. Now, if you most likely have noticed that, but in all of these 4 projects, one thing that comes up a lot is mainly working with data and working with machine learning. So over the next few slides, I'm just going to give a quick introduction to what machine learning is and tell you why, as mathematicians, you should work on that field and why you should join DRDC to work on machine learning. So machine learning, you most likely have heard that name before, whether it's in the news or maybe in your classes, or maybe you haven't heard of it, but it's just simply machine learning, as the name suggests. It's a technique for computers to learn using data. So this field falls under the artificial intelligence umbrella, which is simply mimicking the intelligence of human beings. And a subset of machine learning is deep learning. So in the news, you most likely have heard of AI. Almost all the time when the news is talking about AI, it's actually talking about machine learning, which is companies or industry have developed algorithms that would take in, ingest data. And this could be any kind of data. It could be images, it could be text, it could be sound and voice, it could be data that are not structured, so literally a human being just reporting information, and ingest this data and try to uncover patterns and learn from them. So the next time a new piece of data comes in, it will know what it means. So quick, what does that, what machine learning means? So let's say you are trying to differentiate between 2 pieces of fruit, and you know that if you weigh these pieces of fruit and the weight is less than 140 grams and the length is less than 14 centimeter, that means it's apples. Else it's a banana. So what you've built here is what's known as an expert system, and it actually could be argued that it's an AI because you have transferred your intelligence into a computer by implementing an expert system. And that's the other thing to watch out for, is when the word AI is being thrown around, sometimes what companies are mentioning is talking about are expert systems, which is systems that have been crafted to mimic the intelligence of a human, but they're actually not learning from data directly. But we're talking about machine learning. So this example would, let's say, is an expert system. So, but you want to switch to machine learning because it's the new hot thing. It allows you to explore the data more. The way you would do that is you would take historic data. So you essentially go out, weigh a lot of apples, weigh a lot of bananas, put them into a machine learning algorithm, and then create what's known as a predictive model. From there, as a new piece of fruit comes in, you would weigh it and you measure the length and put it through the predictive model, and the model will say, hey, that's an apple or that's a banana. So it's using historic data for a computer to learn essentially these rules. The way that would look like is you would plot, as an example, you plot all of your inputs, which is a banana and an apple. And here we have, there's a simple plot. And as a human, you could immediately see where you could put some sort of a decision line that will tell you how to differentiate between a banana and an apple. And yeah, that black line, it falls somewhere in between. Now, a machine could do that visually, but actually the way it would work is it relies on mathematical operations in order to determine that line. So as an example, one of the machine learning algorithms is known as a decision tree. And the way it works is it tries to place a decision line that would reduce the entropy of the system. So if you've taken entropy before in your mathematical courses, it essentially calculates the entropy whenever it tries to move that decision line. Another type of machine learning algorithm is support vector machines. The way they work is they place vectors around a random line, and then they try to minimize the length of these vectors if the wrong piece of information is on the wrong side of the line, or maximize the length of these vectors. Another kind is could be KNN, or K nearest neighbors, and this is more of distance metrics. So again, you might have heard that in your math courses, but it calculates the distance on different geometries. So you could have Euclidean distances, or you could have different kind of distances, such as Manhattan or Wasserstein distances. So these are different kinds of distances that could be used in order to try to calculate what's the distance between a decision line, a random decision line, and the distributions, as an example, of the different kinds of fruits. Or you can go all the way down to deep learning, which is neural networks, and that uses a lot of calculus and differential equations in order to try to optimize the algorithm. So if you're doing mathematics, you have seen all of the basis of machine learning more or less, and it's now just the application of these mathematical equations. But so that decision line is there. Now, if a new piece of fruit comes in that's marked in red, and we will say that this is an apple because it falls on the right-hand side of the decision line. So that's essentially what machine learning is, and it could be divided into three main subsections. You could have supervised learning, reinforcement learning, and unsupervised learning. So in supervised learning, that means that the data is available to you to learn from, and it's labeled. So some expert, data expert, usually a human, sat down and went, this piece of fruit is an apple, this piece of fruit is a banana. And from there, you could end up with what's known as classification. It could be image, customer, diagnostics, identity fraud, or regression. And regression is essentially, and instead of having a discrete labels, so a banana or an apple, it's the other way around. It's having continuous labels. So someone sits and labels the temperature, or you measure the temperature as an example, and it's on a continuous scale. And then when you go in and try to predict the temperature, it's a continuous scale. So you're using regression. And regression really uses a lot of linear models. So you might have seen that before in your studies. Another kind of machine learning is unsupervised learning. And as the name suggests, there is no expert labeling the data. It's just data that's available for us. And now we want to understand more about this data. So we could use what's known as clustering. So something like I mentioned is KNN, which is K nearest neighbor. So clustering is trying to divide the data into meaningful clusters that are close together. And by close together, I mean they use distance measures in order to try to create these clusters by the data points that have the least distance between themselves is considered a cluster. We also have what's known as dimensionality reduction, and this is trying to take high dimensional data. So we as humans, we're used to 3 dimensions. Well, 4 if you include time, but we tend to visualize 3 dimensions. But data really could have any dimension. In my research, I work with, as an example, I have 192 features, so I have 192 dimensions. And now trying to reduce these dimensions in order to, first of all, reduce complexity to visualize the data, and also to in order to improve the machine learning algorithm. And some of the tools that are used for dimensionality reduction fall under unsupervised learning. Finally, reinforcement learning, which I would say is the extremely mathematical heavy, because it uses something known as Q learning. If you haven't looked at that, I highly advise you to do. It's quite interesting. It's essentially mimics how a toddler or a young person would learn, which is through trial and error, by providing a reward and by providing a punishment surplus. Actually, well, I say toddlers and young individuals, but let's face it, all humans learn like that, regardless of the age. If you get a reward for doing something correct, you will learn to do that something in that same manner. Examples of where the armed forces are or could use machine learning. So they could use reinforcement learning as an example to train robots to move around. You would be surprised that currently the most advanced robotics out there, which are designed by General Dynamics or DARPA as an example, don't use expert systems. They don't actually use machine learning. They're trying to transition to that field, but they develop mathematical models of how a human being would move, and they put that into a robot. Another application on the right-hand side here, you see a system that is using sound recognition in order to pinpoint and triangulate where a gunfire is, where a shot is. And that system is quite effective because it could notify the armed forces, or it could notify the police, as an example, early on, faster than any human could dial, as an example, 911. It also could be used on the left-hand side here. You see mines. So it's taking pictures of mines in the in the sea and trying to identify whether that is a threat or that's just a piece of styrofoam. So this is using image recognition and computer vision algorithms. On the right-hand side, we could this is known as wargaming, and wargaming is essentially a simulation of an actual war or an operation. Now, typically right now, it's run by human experts who have knowledge of how a certain country would act in a time of war. But with reinforcement learning, you could train algorithms to try different scenarios and come up with the best strategy. Now, the armed forces are exploring all these applications, and it's quite exciting. So if you join DRDC, you might get a chance to work on some of these projects. They're still in infancy, so you get to start to build them from the ground up, which is pretty cool. But machine learning is not all roses and happiness and everything is going well. It has some biases that we need to look out for. Now, the reason I'm going to talk a little bit about the pitfalls of machine learning is that if it's a subject that you're interested in, I want to make sure that you know it's an amazing tool. It's a powerful tool. It's really machine learning is probably where a lot of our systems and our algorithms are going to go to, but it's also something that you need to be wary of, and you need to study on what's wrong with it and how you could improve it. So if you are in statistics, as an example, you might have heard of biases before, a data bias, and so machine learning also suffers from that. So you could have prejudice bias. So the person who's designing or collecting the data or designing the machine learning algorithm could be biased toward one group or another versus another. So as an example, on the right-hand side, if I were to ask you, what's the picture or who is on the left? So this picture essentially, yeah. And you most likely would guess it's Barack Obama. Now, this algorithm was trained in order to take a low resolution picture and essentially up the resolution. And when the picture of a pixelated Barack Obama was put through a system, it ended up looking like a guy on the right-hand side. And you might go, wait, that's not even the right ethnicity. And the reason behind that is because this algorithm was most likely trained on a data set that was collected, might have been collected in North America, which the majority of the population are Caucasians. So that would be known as prejudice bias, as an example, or sampling bias. So you can have other biases such as algorithm bias or anchoring bias. Again, it comes down to collecting data or the designer of the algorithm is pointing the algorithm to give solutions for a certain data set or a certain ethnicity or a certain race or religion. So biases in machine learning is a quite important topic, and the armed forces, and I believe, not sure if there are a lot of people at DRDC are looking at yet, but it's coming up, and it's something that has started to be discussed and heard around the armed forces. Data manipulation, that's something that's coming up, and I'm starting to look at, which is known as adversarial machine learning, which is trying to fool the machine learning algorithm. And you don't want that, because if that happens, then you could have a system that's trying to identify, as an example, friendly forces from the opposing forces switching the answer or making a mistake, which is not really a good thing. So as an example, on the left-hand side, a machine learning algorithm was able to indicate that this is a minivan with a 62% confidence. However, after adversarial crafting, which is by adding the noise you see on the right-hand side, well, an attenuated noise, added to the same picture. And if you look at the picture, they're more or less the same. Like these two pictures to the human eye look extremely similar. However, the picture on the right-hand side, put in through the same algorithm, has identified this picture as Siberian Husky. And as you can see, it's not a Siberian Husky. It doesn't even resemble it. But that level of noise was able to fool the algorithm. So if you go into the machine learning, field, a big area that's coming up, which is something that if you're interested to get in the field, is adversarial machine learning. And I'll highly advise you to start studying in that field or subfield. And finally, context. So you might have seen this picture before. This is a Tesla. that's driving down a highway, and the dot that you see over here, to the human eye, if I were to show you this, you'll probably say, oh, that's probably the moon or an airplane flying or something that's high in the sky. But to the car, this looks like a yellow light. And that's because of context. It misidentified the moon or that light as a yellow light, but it didn't have the context that it was on a highway, as an example. And if it's on a highway, you typically don't have traffic lights. It didn't understand that the angle of that light was pretty high in the sky compared to a traffic light would be lower. So context is another pitfall of machine learning. It's only able to learn from the data that's been provided, but it doesn't have any context from what's outside. So again, another great area if you're going into machine learning is trying to understand how trying to build, whether it's mathematical models or augment machine learning with mathematical models of the world. They'll be able to actually double check itself and make sure that it's whatever it's getting out of the data makes sense. And yeah, that concludes my presentation. Here's my email on the bottom, hamad.abdazi@forces.gc.ca. I'm a new grad at DRDC, so I'm not handling the hiring. David is. But if you have any questions about more questions about like what it's like to work at DRDC, please ask me right now. But if you'd like to email me to get more information, I'm happy to do so.
Thank you very much, Mohammed, so for an interesting presentation. So now we will move to the questions part for David and for Mohammed.
I guess I've got a question for David. Oh, go ahead, Evans. I'll ask after you.
Okay. So my question is, looking at David's background, he has both physics and some mathematics and so on. Also, Mohammed also have something like engineering, which is more practical. Now, if you are in math and you are the pure math part or side, you have a place at the military to work for Canada.
So I can take a first stab at answering that. We have hired people from a range of different mathematical backgrounds at DRDC, at the Center for Operational Research and Analysis in particular. So what matters is if one is able to apply whatever mathematics one's learned to practical real-world problems. So I had no background in operational research per se when I got hired. What I did have was experience solving physics problems for the most part, and a lot of that was analyzing data. So I had some statistics background, but there are other people who have come from pure math background, and in the interviews that we do, it's kind of like an oral exam, where at least when we did them in person, now we do them virtually. We give a number of math problems to people to solve, and depending on how well they do, we hire them or we don't. So we really do look at a wide range of backgrounds. We don't say, you're pure math, so we're not going to pay attention. Definitely not.
Okay.
I'll just add really quickly to David's answer. So my interview, as an example, was mainly asking me questions about how to conduct research and some technical questions on machine learning, because I was hired in that field. But the one thing I would say is anything is based on mathematics. So if you just want to augment your skill set in order to be more applied, I would say learning programming would take you very far. If you have the mathematics down, you just need to be able to program that into a computer, and you're kind of golden, sort of thing. So that's my piece.
All right, thank you.
Ben, did you want to ask your question?
Yes, thank you. So I guess this isn't just a question for David. It's for either of you if you want to answer to Mohammed. I guess my question is there anything in particular you're looking for this round of hiring? Like, in terms of background or knowledge. So just for my purposes, like I'm getting my master's in applied math right now. My thesis is going to be for fluid dynamics, but I worked as an actuary before, and I've got a math and stats degree for my bachelor. So I guess I was just kind of wondering, like, you know, if there's some sort of extra skills I might need to learn or to show, if like you had any recommendations for ways to go with that.
So when I'm scanning resumes, and I guess what I tend to gravitate towards, and I know this happens to other colleagues, is seeing a variety of experiences. Now, having said that, depending on how old someone is and how long they've been in school or in the workforce, that's going to not necessarily, it's going to be shorter the younger you are. And we actually very much want to renew our workforce. We're not looking to hire only people who are 50 plus or anything like that. So like you said, having done some actuarial science, so you've got strong in stats, strong in math, that definitely appeals. I don't look for specific programming languages. So someone did ask that question in the chat. It's nice if people happen to have experience using languages that we most commonly use these days at our place of work, but my opinion, my philosophy is if someone can code in one modern language, they can figure out other ones, and it's not a big deal. And when we hire people, a lot of people who come to work for us spend their whole careers with us, so it's like 30 years. So the amount of time it takes to learn a new computer language is a pretty small chunk of that career, so it's a small investment. So we're most interested in hiring hardworking, smart people who work well with other people. The specific, did you take such and such a course, or did you learn this particular programming language, is much less important. Anything to add, Mohammed?
Yeah, absolutely. So I can only speak about my experience getting hired, not hiring someone. The questions I've been asked about was mainly talk about my projects. So what I got from the hiring process, that my hiring committee was looking into understanding the way I think and trying to think out loud. What is a project that I've done before? What steps did I take to resolve any issues that came up in the project, and also looking at the way I communicate the motivation, the development, and the outcomes of that project. So these are the things that I was mainly asked about in my interview. I did not have a lot of technical questions, just a couple of questions just to verify that. So I was being hired for machine learning just to make sure that I actually know machine learning. But from a technical perspective, it wasn't heavy. It was more heavy on can you think and can you communicate what you're thinking. I would say that was what I got from my interview. And of course, David is on hiring committees, so he knows more. In terms of programming, yeah, if you can program as an example in C++, probably transferring that to, let's say, Python or MATLAB is doable. Personally, the languages that I use is mainly Python, specifically for machine learning, and right now that I use for my work, just because it's more accessible. It doesn't require any extra licensing as compared to, let's say, MATLAB. I've heard people using R, which is really useful if you're doing more on the stats side. And even some of the machine learning algorithms are available in R. So really, if you know one programming language, the other should come easily to you.
One thing I'd add, since you mentioned it, and I failed to before, about communication ability, that's very important. We do include that as part of the interview process, and both for writing and for oral communication. You have to communicate with a range of people in this job, not just other scientists or mathematicians, but also people who work in the military, because you have to be able to talk to the people who have the problems that need solving, figure out what they're getting at, translate their problem into something mathematical that you can solve, and then you have to explain it back to them in terms they can understand. Some of them might have degrees in something technical or graduate degrees in something technical, but most of them don't. So someone who can explain complex stuff in relatively simple terms is going to be more successful. Is going to be most successful where we work. So if you do any outreach activity to schools or stuff like that, I definitely notice that. I pay attention to that. Over.
Excellent. Excellent. Thank you.
Thank you.
So I would like to thank Mohammed and David for very interesting presentations. So this was a good insight for us into the life of DRDC. And it's an inspiration, right? So for us professional mathematicians, we train students, and it's good to know that that this training goes and gets applied for good use and good cause. Thank you very much, and I appreciate very much you coming here and speaking to us. And I hope we will do this sometime in the future as well. Thank you.
Thank you very much, Yuli, and thank you to everyone for your patience and listening to our talk. And hope to hear from you soon with some CVs.
Thank you.
All right. Thank you, and goodbye, everybody. Have a good evening.